Those are the two forms of mechanical energy. I might emphasize right now that work is not a form of energy. Work is a loss or gain of energy. It's taking energy in or out of the object. I'll show you how that works right now. Very simple, context-free situation, so we don't get confused about a cat having a tail like we did once. We'll just have a box, and we're going to lift the box. The box is mass M, sitting on the floor. It's not moving. It has no height, so there's no kinetic energy. There's no potential energy. There is no energy, period. Total energy, which we'll use the letter E to denote, is the total kinetic energy, which we will denote with KE, I've decided, instead of just K, plus potential energy, PE. Those two add together to give you total energy. So when the box is on the floor, no energy at all. Then you lift the box up. Now it's a height h above the floor. When it's up there, it has potential energy. The potential energy is mgh. As long as you're holding it, there's no kinetic energy, but there's that potential energy. So we went from point 1 to point 2, and it went from having zero energy to mg times h of energy, the mass times little g times h. Remember, little g is 9.8 meters per second squared. And so that's the energy at point 2. Here's a very important intermediate consideration. How did the box get from the floor to up here to point 2? You lifted it. How much force do you need to exert on that box to lift it? Remember, it's the force of gravity, the weight of the box. If something weighs 10 pounds, you need 10 pounds of force to lift it. We're in SI units. So if its weight is mg, you have to exert a force of mg in order to lift it. So the work done lifting the object is force times displacement. The displacement is h. The force that you need to apply to lift mass m is m times little g. So the work done lifting that object is mg times h, which is exactly the same as the potential energy that it has up here. This is what work does. You start with zero energy, it's just sitting there. With work, you inject energy into the object, and now it has an energy of mgh up at point 2. That's what work does. It can inject energy in. Or if the work is being done by friction, it can remove energy from the object. But that's what work does. It takes mechanical energy in and out of an object. So let's drop this object and see what happens when it arrives at point 3. So it has purely kinetic energy there. There's no more height, so it has only 1/2 mv squared when it gets to point 3. Energy at point 2 was mgh. Energy at point 3 is 1/2 mv squared. You know, we can figure out what v is. We learned how to do this when we did kinematics. If you drop an object at distance h, how fast is it going? It wasn't totally straightforward. We did it as a two-step problem. First, you find the time spent falling, and then if something falls with an acceleration of g for that time, you can find the velocity it's going at the end. But I did at one point give you guys a little expression that you can rely on called the v-squared equation. That takes it into a one-step calculation. This comes straight from Galileo. A velocity squared is the initial velocity squared plus 2 times acceleration times displacement. The initial velocity is 0 because you're dropping it, so you could say the speed squared when it hits the ground is 2gh. That's a keeper for you. If you drop an object a distance h, the speed that is going after it's fallen that distance h is the square root of 2gh. I've put this on the board for us before. It's the free fall velocity equation. Again, you could figure this out in a two-step problem where you ask yourself, how long does it take to fall, using the displacement equation, and then ask yourself, how fast is it going after that much time, using the definition of acceleration. So put that into 1/2 mv squared. If v squared is 2gh, then 1/2 mv squared is 1/2 m times 2gh. The 2's cancel, and the kinetic energy the box has when it hits the floor equals mgh. So they're all the same. You do a work lifting that box equal to mgh. At the top there it has a potential energy of mgh, and it's only potential, and then you drop it and it hits the floor, it has only kinetic energy, which happens to be equal to mgh. They're all the same. The energy at point 2, when you're holding it way up there, equals the energy at point 3 when it hits the floor. And that also happens to be the energy that was injected into the box initially by work done by you. So this all balances together in something called energy conservation. So let's summarize what we just saw. You took a box on the floor, it had no energy, you lifted it and did a work equal to mgh, lifting it, force times displacement. Force of gravity, mg, times displacement, h. And so that was the work done lifting it up to point 2. You held it at point 2, where it had a potential energy equal to mgh. That's the new equation that I've given you for the type of potential associated with gravity. mgh, mass times little g, times how high above the floor something is. And then you drop it, and it hits the floor with lots of kinetic energy. The kinetic energy, which is defined as 1/2 mv squared, is easily shown using Galileo's equations of motion to also be mgh. I want you to know that when you drop an object, all of its potential energy is converted into kinetic energy. And in order to get the object up there, you had to do work that equals the amount of potential energy it has. Let's do an example that puts it all into a realistic scenario. So you throw this coin straight down. So I give it a hard toss, straight down at 4 meters per second. 35 meters above on a bridge, so it's going to hit the water in the river below. As the coin goes from your hand to the water, how much work does gravity do? That's part A. And then part B is how fast is the coin going when it hits the water? You might recognize this problem from way back when we were doing projectile motion. And I asked you guys, if you throw something straight up or straight down, in which case is it going the fastest when it hits the water? And we concluded it doesn't matter. You can use the principle we just covered with energy to show the same thing. So when you drop the rock, it has a force of the force of gravity, which is mg, but it points down, so I'm going to call it minus mg, because the force is downward, it has to be negative. And it has a displacement delta y, which is minus 35 meters. So you can calculate a number. Mass is 5.5 grams. Remember, you divide by 1,000 to get kilograms. 0.0055 kilograms times the acceleration, which is minus 9.8. The acceleration is minus g, times delta y, which is minus 35 meters. And you get 1.9 joules of work done on the coin by gravity as it travels from your hand to the ground. 1.9 joules is the amount of energy that is added to the coin as it proceeds from your hand to the ground. That work is also the change in kinetic energy. That's the work energy theorem. Remember the work energy theorem? If you do work on something, its kinetic energy changes by that amount. So the 1/2 mv squared final minus the 1/2 mv squared initial is the change in kinetic energy, and that's also the work that's done. Some of you may be missing this algebra here, so let me put in a step here. The change in kinetic energy is the kinetic energy final minus the kinetic energy initial. So that's 1/2 mv final squared minus 1/2 mv initial squared. This is just factoring out the 1/2 m. That's the work done, the change in kinetic energy. So put in some numbers. So the work done is 1.9 joules. Mass is 0.0055 kilograms. Initial velocity is given as 4 meters per second. And so we can find the final velocity. All these things are unknown. Make sure you can do the algebra here to calculate the final velocity from this expression. So you got to go 1.9 times 2 divided by 0.055, add 4 squared, or 16, and then take the square root of all of that. Those are the operations on the calculator. Try it now. And you get a final velocity of 26 meters per second. We will pick up next time, again with the same idea that energy is conserved, and we will apply it to various situations. We'll also take a look at potential energy in other contexts, such as springs. So if I compress a spring, it has a lot of potential energy because when I let go, it launches things. So we'll look at that. We'll look at how that works a little bit next time.